Hello everyone, welcome to the last class of this semester of fluid mechanics. And in this class I'm going to review some questions and solve some example questions which helps you through the final exam. The first question is going to be for chapter 4. Since I solved more questions for chapter 5, so I'm going to skip it, but we'll solve questions for conservation of energy in the pipe flows, which is also covered conservation of energy in the control volume because it's part of it, but two questions for chapter 8 and one question for chapter 4. That thing, it means that you have to review these two chapters also for the final exam. Okay, so the first question is for chapter 4. The velocity field is given u, v and w. It asks you that what is the volumetric dilatation rate, and interpret the results. But it means that what you will find out by finding the volumetric dilatation rate. The part B asks you that what is the rotation vector, and part 3 asks you that the flow is rotational or rotational. So let's solve part A and do the analysis part by part. So in part A, it asks you to find volumetric dilatation rate. Okay, so first you have to check the notes to make sure that you correctly know what is the equation for that. Is the gradient dot v. So if we're going to answer this question, that what does it mean if you find out dilatation rate or gradient dot v. If it's 0, means the flow is incompressible. And if it's not 0, is compressible flow. Okay, so part A, it asks you that find it. Okay, so the equation is gradient dot v is equal to partial derivative of x for u, partial derivative of v versus y, and partial derivative of w versus z. Okay, and you have to find out what is the answer for that to make sure that the flow is incompressible or compressible. So for gradient dot v, I can replace this with u. The u is x squared plus y squared plus z squared, that is given, plus round over y. For v is xy plus yz plus z squared, plus partial derivative versus z for w, which is minus 3xz minus z squared over 2 plus 4. Okay, so gradient dot v, which is our dilatation rate, it has to be, for this term, just this first parameter term has a derivation, but the other one doesn't have, so these two are going to be 0, and the answer is 2x, plus for this term you only have x plus z, so x plus z, plus for this term versus z is going to give you minus 3x minus z. Okay, so if you add this to that, then which is 3x is going to cancel out with minus 3x, and z is going to cancel out with the other z. So this is going to be 0 in all the points or in all the domain. 3x minus 3x plus z minus z is going to be 0. Meaning of that is the flow is incompressible everywhere, or total is compressible. So sometimes it's possible that you give the x equal a gradient that v equal to x. Okay, so it means that if x is 0, the flow is incompressible, but we don't care about the points. The flow in total is compressible. So sometimes possible that you find out in a range of x or for a single point in the domain you will have incompressible flow there. Okay, so it's not working when you are doing the analysis on the whole flow. So you can say that in general is incompressible. Okay, so that's what we have in part B for finding the rotation vector. So rotation vector is omega, right? And the equation for that is one over 2 the curl of velocity. The curl of velocity is equal to the determinant of ijk round over x z and ubw. Okay, you can write this to remember that if you can get the determinant for 3x3 matrix. If you don't know what is that, you can because that's a rule for it, you can say that I times and get rid of these two lines, this row and the column, and then it's going to be rho w over rho y minus rho v over rho z. Then this is going to be your first component. It's only if you don't need to remember the whole equation, then you can say make it simpler by understanding the determinant. But if you want to have a note, so you will have the equation and don't worry about that. This is going to be the whole equation is going to be something that I'm writing right now. It's going to be over z, that's the I, plus 1 over 2 u over z minus w over x j plus 1 over 2 rho v over x minus rho u over rho y. That's okay. Okay, so the whole this term is omega x, the second term is omega y, and that's omega z. Okay, so that's the equation for rotation vector. But since you are going to calculate those terms separately, then I will write it like something like that. I'll write the equation for each of those, because the one with the I is omega x, then it's going to be 1 over 2 rho over rho y. For the omega is minus 3 x z minus z squared over 2 plus 4. Then the second term is minus over on z xy plus yz plus z squared. Then also second term have more space here, so y is 1 over 2 partial derivative versus z times x squared, which is u, y squared plus z squared, minus partial derivative versus x minus 3xz, which is or w, minus z squared over 2 plus 4. And the wz omega z is going to be 1 over 2 partial derivative of x for v, which is xy plus yz plus z squared, minus partial derivative versus y for u. Okay, to make sure you're writing correctly, you have to know that omega for the omega, which is your rotation vector, u, v and w only one time comes in the first term and one time should be shows up in the second term. For example, here is u as a in the first term and only one time in the second term. This is w and here is your v. So v also in the first term, it shows up here as the second term, and here is your w and here is w. You see that one time comes for the first term and one time as a second term. And for the x one, when you are doing the calculation for the omega x, you have to make sure that this partial derivative is for the other two directions, so y and z, and always are the difference is that, so for the first one, which is the partial derivative of y, you have w, and for the z you have v. Here you have z, you have to use u, and for x1 you have to use w. So if you check that what is the characteristic of the equation, you make sure that, because the partial derivative, sometimes the students make mistake in the just copying the equation, so you have to check it out to see that what exactly is repeating in the equation. Then you will have better understanding, and also you make sure that you're not doing or not losing points because of wrong equation. Okay, so if I want to just finalize the answer and find out what is the equation, omega x, here to see both of them. So omega x is equal to, this is going to be 0, the second one is 0, and the third one is 0. So it's going to be 1 over 2, 0 plus 0 plus 0, because none of those have y in it, minus, for this one is 0 plus y plus 2z. Okay, then the final answer is for omega x minus y over 2 minus c. For the y term, that you have 1 over 2, this is not a function of z, so it's going to be 0, 0 plus 2z minus 3z, another minus because it has minus 3z, so it's going to be minus 3z, and the other two terms are 0. Then this is going to positive, plus 2z is going to be 5z, so it's going to be 5 over 2z. Now for the z1, the same calculation, so it's going to be y plus 0 and 0 minus 0, 2y and 0. Then this one is going to be minus y over 2. Okay, so you found out what wx, wy, wz, then the only thing that left, you have to write it as a vector, because the rotation vector is requested. So wxi plus omega yj plus omega zk, it has to be minus y over 2 plus z I plus 5z over 2 j minus y over 2 k. That's your rotation vector. So part C asks you that is the flow rotational or irrotational. So we have to check the omega. So omega has a terms as a function of x, y, and z. So it's not always 0, then w omega is not 0 everywhere, right? Because in the single point you can find out a point like z is equal to 0 and y equal to 0 and any x, like a line in the space or domain, 3D domain, that it could be 0, but we don't care about it because our flow is 3D. So it's not 0 everywhere, then the flow is not rotational, irrotational, is not irrotational, or you can say that the flow is rotational. That's the interpretation of that. So when omega is 0, or in simple word, you can only find out what is the curl of V. Okay, so if it's 0, then the flow is irrotational. If that's not 0, means that omega is not 0, then you will have rotation vector, then it's going to be rotation. So you will have a question exactly or similar to it in the exam. You will have to check the dilatation rate, the volumetric dilatation or the divergence of the velocity to show that the flow is compressible or incompressible, or you have to find rotation vector to find out the flow is rotational or irrotational, and also sometimes may ask you to find the streamlines, or sometimes finding the acceleration field from that, and all of those are covered in chapter 4.
Sorry.
Okay, so that's the first question. In the second question that I'm going to review today is for chapter 8, which is the flow in the pipes. So this question is for a horizontal tube or pipe, and the water at 20 degrees flows through this horizontal pipe. So first I will show you how we always write or draw a figure for that if the question by itself doesn't have, to make it numbering and also shows that how the flow passes. So it's a horizontal pipe, or tube, and the flow comes in from one side. The diameters of that is given as 1 millimeter, so 10 to the power of minus 3 meter for D. Okay, what else is given? The length of that is also given as 1 meter, And another input that you need is the nu of the water, which is at the 20 degrees 10 to the power of minus 6 meter square over second, and mu of water at this temperature is 10 to the power of minus 3 Newton second per meter square. What else is given as an input? It's also given that it attached to two pressure taps with a distance of 1 meter. So it means that the flow is inside of the pipe, but the pressure at point 1 for input and output are different. So it means that you have a different pressure over there. Okay, that's all is related to that. So let's write the assumptions. So the first assumption is that the flow is laminar. So it asks you to find maximum pressure drop, but allowed if the flow is laminar. So flow is laminar. What else? Pressure at point 1 and 2 are not equal. So what does it mean? It means that you have a delta P pressure drop which is not 0. And why it's not 0? Because you have losses, right? If you don't have any loss there, then you can apply Bernoulli and say that the pressure are the same. Doesn't matter that both of them are static pressure or gauge pressure or atmospheric pressure. You have to mention that the pressures are different, right? And also in this type of the flows that you don't have any pressure drop over there, then if you assume that these two are the same pressure, then no flow going to pass over it. Because you have losses, and it's not possible in thermodynamics that you go through velocity of 1 to the velocity of 2 with this, that these two are the same, and pressure 1, pressure 2 are the same, but you also have a losses here, so you have to have work, or you have to have a moving forward force like delta P. So from high pressure to low pressure. What else you can assume here? You can assume that the flow is fully developed, because if you assume that is an entrance, then the flow is not fully developed, then you cannot solve this question. You have to assume that the flow is at least fully developed to make sure that the alphas are the same when you apply conservation of energy or finding delta P. So what else? If fully developed flow is that, then average velocity input and output are the same. Why we are talking about the average velocity? Because you know that the flow in the pipe is not uniform. Then you are talking about the average velocity to make sure that m dot 1 and m dot 2 are similar. So when applying conservation of mass, m dot 1, one input and one output, then m dot 1 has to be equal to m dot 2. So rho AV in only when you can use rho AV when they use the average velocity. So rho AV 1 bar and A1 absolutely, because the diameter of that is constant. Then rho A1 V bar 1 is equal to rho A2 V bar 2. So the constant properties, these two are similar, A1 and V2 are similar, so V bar 1 is equal to V bar 2. But since this is simple, we don't apply conservation of mass, and you don't need to show it by applying conservation of mass, but you can write it down as an assumption because it's easy. Okay? So let's go for finding delta P. What's delta P? Delta P is the pressure drop, right? So if you check the notes of the chapter 8, delta P for laminar flow, delta P's equation is given. So delta P is for a round pipe with the circular cross-section area is 32 mu L V bar or V over D squared. Okay, so that's the equation for delta P. So the other question is that it asks you to find delta P maximum pressure drop allowed if the flow is laminar. So at first it asks you to find delta P, but it doesn't give you V bar. In this equation you have 32, which is constant, mu is given, d squared d also given, and a length of the pipe is given, but V bar is not given. You only have this assumption that the flow is laminar, and you have to find delta P maximum, which happens when the velocity is maximum, because these are all constant, right? You don't change the pipe dimension, so L and D are constant, mu the flow is constant, so you are not going to change anything except that the velocity is constant, maximum. So what exactly makes the delta P maximum? When the velocity, because velocity increases, then delta P increases. These two are correlated. Okay, so now the question is that how we can find the maximum velocity or velocity of the pipe. We don't have any information like the Q, m dot, nothing is given. So how we can find it? Using the Reynolds number. Why? Because Reynolds number critical is 2100, and the maximum velocity, that we keep this assumption that the flow is laminar, it means that we need to find the maximum velocity, that if you multiply it by rho d, because the rho vd is the equation for Reynolds number, right? Rho d times velocity over mu of the water, okay, it has to be equal to the critical Reynolds number. That's why if you change these two with nu, then you can say that 2100 for the Reynolds critical, it has to be equal to nu of water times V of the max over D of the pipe. Okay, then V of the max can be easily found by 2100, which is the critical number for that, the maximum critical Reynolds number that you can have to have a laminar flow. What is the nu of water is given as 10 to the power of minus 6 meters square over second, and the D is given as, oh, I made a mistake here. So here the Reynolds is equal to rho Vd over mu, so it's going to be nu of water times V of the max over D. That's D has to be in top, and mu over rho is nu, so it's going to be diameter of the pipe times velocity of the max over nu of water, right? So if you want to find V of the max, you can multiply 2100, which is your Reynolds critical, times nu of water over D. Nu of water is 10 to the power minus 6 meters square over second, 2100 is Reynolds critical, and D of pipe is 10 to the power of minus 3 meter. So if you cancel out the units, you will see that the answer is meter second, and V max would be the maximum velocity that you will have still laminar flow. Is going to be, using calculator, is going to be 2.1 meter per second. That's the way you can find out the velocity. So if that's my equation for equation 1, then how can I find delta P of the max? By plugging V max in the equation. The rest of those are given. So delta P of the max, maximum pressure drop to allow to have a laminar flow, is equal to 32, using the equation 32 times mu of water, which is 10 to the power of minus 3 Newton second per meter square, times L, which is 1 meter, times velocity, which is 2.1 meter per second, over the d squared, which is 10 to the power of minus 3 meter to the power of 2. Okay, then delta P of the max is equal to, use a calculator, is 6.72 times 10 to the power of plus 4 Newton per meter square, or Pascal. So check the units. Newton, it has to be here, nothing to cancel out that. Second is cancel out with second, meter square with meter square, and you have another meter square on the denominator, so the final units also match. You will find it out, part A, what is the maximum pressure drop allowed if the flow be laminar. Okay, so part B asks you that, assuming that you are taking care of a manufacturing pipe. So in the manufacturing pipe, all the pipes are not similar. Sometimes you have a tolerance. Absolutely, in manufacturing you will have tolerance in the manufacturing process. So the diameter is not always exactly 1 millimeter. Sometimes it's 1 plus 0.1 plus tolerance that you have. So the tolerance could be 0.1 millimeter. Then it means that if you have a new pipe, then diameter of the pipe could be in a range of 0.9 millimeter to 1.1 millimeter. Okay, so it's not always exactly 1 millimeter, but it is in a range. So it's not going to be less than, because that's the tolerance. It's not going to be less than 0.9 millimeter and not higher than 1.1. So now it asks you that, the question asks you that if we assume that this is our tolerance for the diameter, and based on this uncertainty in the manufacturing process, what is the maximum pressure drop allowed if it must be assured that the flow is laminar? So we are still going to keep our laminar flow, but with the minimum and maximum diameter. Okay, so at first let's write down the equation, because the equation doesn't change. Delta P maximum allowed is equal to 32 mu L V bar over D. Okay, D of the pipe. So you will have, I can ask you this question, that how we can make delta P, or what is the relation between delta P or pressure drop and the diameter. So you can see that if we increase the diameter, then delta P is coming down, right? If you are going to find out what is the, if you find out what is the limit, the maximum allowable pressure drop, then you have to make the diameter minimum, right? So if you have a minimum diameter for the pipe, then the delta P is going to be maximum for you. Okay, replace V bar max with the critical number that you have. So it's going to be 32 mu L, and this is going to be Reynolds critical times Reynolds is rho V D over mu, right? So it's going to be mu, or nu velocity maximum is going to be nu times D times Reynolds over D, right? So I can replace that by Reynolds critical times nu over D and D squared. Okay, find out what is the maximum allowable diameter, means that what is the maximum allowable diameter for the maximum diameter, right? So if I get that the delta P max allowable, delta P max allowable times which is equal to 32 mu times L, okay, so times V bar, which is the velocity, and over d. Okay, so if I write it down like this, that d times delta p of the maximum allowable delta p over 32 mu L is equal to, or V bar. Okay, so you are going to find the maximum number allowable for delta P to have the maximum amount for the velocity, right? So if you are going to find out what is the maximum amount allowable for velocity, that this is going to be related to Reynolds number, and because of this Reynolds number you will have the maximum number allowed to have a laminar flow. Then your D has to be maximum. If you check it out for the maximum number D that in the manufacturing process you will have, then you could find the maximum delta P available that are allowed. Okay, so that would be the limit that you have to check for. So delta P max allowed then can be find out by the equation as 32 times 10 to the power of minus 3 Newton second per meter square, which is, or mu times L, which is 1 meter, and V bar max, that we don't know what is that, but we can find it by critical Reynolds number, over 1.1 times 10 to the power of minus 3 meters square to the power of 2. Doesn't have power 2. It's going to be meter. Okay. Then what's next? Finding the V, right? So V bar max can be found out by the Reynolds number times nu over d, right? So V bar is going to be equal to, V bar max is going to be 1.91 meter per second, and if you plug in inside of that, then delta P max is equal to maximum allowable delta P is going to be 5.05 times 10 to the power of 4 Newton per meter square, which is what Pascal. That's a little hard question, I know, but in totally in mechanical engineering, your design is going to end up by manufacturing process. So you need to know what is the uncertainty in the manufacturing process and apply that in your design, because you have to make sure that what would be the dimension of the pipe, at least to make sure that plus or negative, this uncertainty that you have in manufacturing process, that the whole pipe system that you are designing is be less than or not closing to the turbulent flow. Because most of the time in the pipe systems you don't want to have a turbulent flow or transitional flow, because the most of the parameters are changing and you have a different status of the flow. So if you want to make a design based on the if you want to increase the mixing, enhance the mixing and the heat transfer, then you will need to be in the transient or fully developed turbulent flow. But if you are in the just transferring energy or transferring the flow from one point to other point, you don't want to have dissipation of energy because of the turbulence. So you want to have a maximum allowable delta P, which is a pressure drop, and another maximum velocity is maximum velocity that is allowable to have that maximum pressure drop in a way to be a stay in the laminar flow, because you're not going to do the heat transfer by transferring the fluid. You're doing that by you're using the pipes only for transferring the materials or the fluid or chemical inside the pipe system. So for this pipe system, that the pipe diameter is 1 millimeter, it asks you to find out what is the maximum level pressure drop to have to stay in the laminar flow based on the manufacture process that you have. So that's the second question that we talk about in this class. So let's move on the other question, which is for the pipe system but complex number of the pipe. So 2 repeating parts. So you have in this question you have a tank, a pressurized tank that the air is in 65 degree, and the pressure is also given as a gauge pressure equal to 3500 of the gauge pressure of Pascal, and you have a series of smooth pipes. So it's smooth. You have pipe 1 and you have pipe 2, right? And I put 0 and 3, which is the atmospheric pressure here at 0.3. Okay, so I put the names there, but what it asks you to find, it asks you to find what is the volumetric flow rate through these pipes. If you write it down, what is the assumptions? Assumption is given as steady. One, the flow is steady. Second, the flow is incompressible. Third is constant properties. And also minor losses is negligible. If you remember, minor losses are because of the intern, for example, interns here, here, and if you have a bending which is not available here, so it's going to start with the entering process from this, the gauge tank, to the first pipe, and also from first pipe to second pipe. So this is going to be negligible. Okay, so in volumetric, to find the volumetric flow rate, which is or Q, if you check out the last part of the notes in chapter 8, we'll talk about that if you have a series of pipes, then Q total is equal to Q1 equal to Q2, right? So it means that the flow rate that passes over pipe 1, pipe 2, and is going to be ended up here, all those are similar. So it means that AV, which is our volumetric flow rate equation, then is equal to A1 V1 and is equal to A2 V2. Okay, that's also the conservation of mass. If you assume that the control volume is inside the pipes from here to here, then this is going to be, if you assume the control volume, part of control volume here, one of the surface, and the other surface here, then the flow rate that comes in is going to be A2 V2, and the one that goes out from control volume, if you put the surface here, there's going to be A1 V1, or A2 V2 equal to A1 V1. So V1, you can find the relation between V1 and V2 because the diameter of the pipes are given. And also make sure that you correct it because it's centimeter, not meter. Okay, so V1 is equal to V2 times A2 over A1. Then is equal to V2 times D2 over D1 squared. I get rid of the pi over 4. Then V2 is equal to 1.25 centimeter over 2.5 centimeter to the power of 4. This is going to be 1 over 2 and then V2 over 4 finally. So V1 is V2 over 4. So you find one equation which is the relation between V1 and V2. So but the problem is that none of those, V1 and V2, are not given. That's the problem. So you are going to find the Q, and if one of those are given, then you don't have any problem because V1 is given and you can multiply that by A1 because the diameter are given, then you can find it out. But it's not given, none of those, not V1 and not V2. So you need another equation to find it out. At least you have at least two equations and two unknowns and find it out what is the V. So one of these are enough to find out the Q, because the Q1 and Q2 are equal. So applying conservation of energy between point 0 and 3. Why? Because point 0 and point 3 gives you more nouns in applying your conservation of energy. First, pressure at tank is given, and also you know that the output is pressure, atmospheric pressure. So if you apply the gauge pressure between these two, then you can assume that pressure here is 0. Also, because it's a huge tank, you can assume that the velocity at point 0 is 0, right? Also, Z1 and Z2 are similar. Then you can cancel out most of the terms in conservation of energy. Okay, so what can we assume? We can assume that V0 is 0 and V3 is almost V2. Why? Because the velocity that if that's V2 in the second pipe and V1 in the first pipe, then V3 is almost V2, right? Because coming here, the V2 are constant all over the pipe, and output velocity is the same as the velocity that you have inside the pipe. And absolutely because you assume that the losses in output and entering of the pipe are 0. So V3 is almost V2, and also since it's a horizontal pipe, you can assume that Z as 0 and Z3 are similar. Okay, what else is given? So P0 is given. We will calculate that. Okay, so for now just know that it's given. P3 is atmospheric pressure, and you can assume it's 0. Okay, and alpha 3 alpha 1 doesn't matter what is alpha 0, but alpha 3 you can assume that it's uniform flow when it's going out, right? So by this assumption and conservation of mass, conservation of energy, then P3 over gamma plus alpha 3 V3 squared over 2G plus Z3 is equal to P0 over gamma plus alpha 0 V0 squared over 2G plus Z0 plus HS minus HL. Okay, so what can we cancel out here? First, we can say that Z0 and Z3 are similar. Then we assume that V0 is 0. And also we can cancel out this term because P3 is P atmosphere. And alpha 3 is 1. Right? Then the only terms left is V3 squared over 2G. What else? There is no work here. It's going to be 0. Right? So if we rewrite this equation and bring the HL or head loss the other side, then P0 over gamma is equal to V3 squared over 2G plus HL. Okay, but again from the last part of the chapter 8, we know that when we have a smooth pipe but in series of the pipes, then the head loss is going to be equal to head loss for pipe 1 plus the head loss in pipe 2. It's like resistance in the wires, right? So now we can rewrite the equation as P0 over gamma, which is rho 0G, right, is equal to V3 squared over 2G plus HL1, which is F1 L1 friction factor and length of the first pipe over D1 times V1 squared over 2G plus F2 friction factor for the second pipe. These are given in the question. So L2 over D2, these are also given, L1 D1, L2 D2, length and diameter of the pipe. So V2 squared over 2G. why we are ending up here? Because we want another equation between V1 and V2. So we know what is the different relation between V1 and V2. Only we need one of those, and also we know that V3 is equal to V2. V1 is also V2 over 4. Alright, so we find it out from conservation of mass, and here we can rewrite this equation as P0 over rho 0g is equal to V2 squared. Instead of that, we can replace V2 squared over 2g plus F1 L1 d over d1. Instead of V1, I can write it down with V2 over 4 to the power of 2 over 2g plus F2 L2 over d2 times V2 squared over 2g. Okay? We'll keep this term here is equal to extracting V2 squared over 2g from all the terms. Right? So this is going to be 1 plus F1 L1 d1 times V2 squared over 2g is going out, so 1 over 16 left, plus F2 L2 d2 and times 1, right? That's what's left. So you can find it out V2 as long as you know what is P0, and you multiply each side by 2g and then over this term. That all are given, okay? But if that's your main equation, still one of those are unknown. That's rho of the gas. Rho of the gas is not given, okay? So you can use the thermodynamics equation for the gases. So from thermodynamics, the rho 0 or T0 are equal to pressure for the gases. Then rho 0 is equal to P0 of the gas times RT0. Rho 0 you can calculate it by P0, which is 3500 for the gauge, plus 101 325 Pascal for the atmospheric pressure. You need to have a total pressure here of the gas to apply the equation in thermodynamics, right? So that's your pressure. R is given as 287.1 joule per kilogram Kelvin, and temperature, it has to be Kelvin. It's given as 65 degree, so plus 253 is going to be your Kelvin equation, okay, in Kelvin. Then rho 0 is going to be 1.08 if you do calculation, then kilogram per meter cube. Okay, so you find it out rho 0, then you can plug in the equation. But before that, we are going to find out what is the velocity, right? So I will write the equation as v square v2 and get square t of p0 over rho 0g times 2g over 1 plus 1 over 16 L f1 L1 d1 plus f2 L2 d2. I'll just rewrite the equation, main equation based on the v2, because that's what we are going to find it out. Then I can cancel out the g's and replace v2 is going to be square t of 2 times the p0. Here p0 is gauge pressure because you applied based on the gauge pressure in one side, and the gauge pressure at point 3, which was the atmospheric pressure, you assumed as 0. So here you have to apply based on the gauge pressure, which is 3500 Pascal and 1.08 kilogram per meter cube for the rho, plus 1 times 1 plus 1 over 16. F1 is given as 0.023 times length of the pipe, both of them are 6 meter, over D1, which is 0.025 meter. That's the length for the pipe 1, the diameter for the pipe 1. Plus, for the pipe 2, you will have F2, which is 0.015 is given, times 6 meter of length over 0.0125 meter. That's V2, 2 times P0 from here. Rho 0 you calculated up, so it's going to be 1.08 kilogram per meter cube, times 1 plus 1 over 16 times 23, which is your F1, friction factor for the first one, and times 6 meter, which is length of the pipe. Also second pipe is also 6 meter. That's the diameter for the second pipe, that's the diameter for the first pipe, and this is also given as a friction factor for the first pipe. Then using this and using calculator, then V2 is 27.54 meter per second. So when you have V2, then you can find the Q total, or the volumetric flow rate from each of those that are similar is going to be equal to Q2 and also Q1, and is equal to V2 times A2. V2 is given, but you can assume that pi over 4 D2 squared times V2 is Q, right? So then Q2 is going to be equal to pi over 4 times 0.0125 meter, diameter of the second pipe squared, times velocity that you find it out, 27.54 meter per second. Then the Q2 is going to be equal to 0.00368 meter cube per second. That's your final answer for the Q. But let's check it out, that what is the Reynolds number here, because you know that the friction factors are for the laminar flow is 64 over Reynolds, right? So you have equation for that, but in this question is the friction factor are given as two constant number, right? So let's say that are the flow turbulent, that the question decided to give us the friction factor or not. So for the second part, I will calculate the Reynolds number, which is V square V2 D2 over nu of the air. Okay, so if you apply this, then 17,230 would be your Reynolds number. That is more than critical, which is 4,000, and the flow is fully turbulent. That's why you don't need to check it right now, because the question didn't ask you that the flow is turbulent or not. But when the friction factors are given, and it didn't give you, if it's not given, then make sure that check the Reynolds number to make sure that the flow is laminar or turbulent. Then if it's laminar, then you can say that, okay, I have an equation for that, because 64 over Reynolds is going to be your friction factor, and also you need to calculate Reynolds number because you're going to put it there and find the friction factor. But if the Reynolds and if the friction factor are given, you can expect that the flow is turbulent, because if it's not turbulent, then it doesn't make sense for us to the question give us the friction factor. So you can check it later that finally the velocity that you found is going to be ended up with the turbulent flow. If not, then you can say that maybe something is wrong in my calculation. So I hope these questions and reviewing these chapters help you for the exam. This would be the last class, and I have another office hours Wednesday, and I will try to be available during the day for the final exam. So final exam is started at 2 p.m. Eastern time, and 3 hours, you will have 3 hours time for the final exam, and I hope you can solve all the question plus the bonus question, and get the full score in this exam. Have a good one.